Hello everyone. So firstly, a warm welcome from Expedia Inc. And we're delighted to be hosting the ISG London chapter. The ISG London chapter will be hosting more events going forward, and we'll be recording them when we can. Our speaker tonight is Professor Kenny Paterson, who's a professor at Royal Holloway, as you will know. And he's also one of the researchers in the team that discovered the Lucky 13 TLS vulnerability, and which is actually an important topic these days, as quite a few of you know. Today we have a mix of Expedia developers and ISG security researchers and practitioners, so it should be an interesting discussion. And so, please welcome Professor Kenny Paterson.
I have a bottle of beer, I have a microphone, and I have a slide clicker. It's hard to carry them all at once, so what should I sacrifice, do you think? The mic? I'm going to put the mic down. I'm very used to projecting my voice to the back of auditoria, so it shouldn't be a problem reaching the back of the room here. Is that going to compromise your recording, though, if I don't use the mic?
I don't think so.
Okay. I'm much more comfortable with these in my hands. So thanks very much to the organisers for organising, and to Expedia for inviting us here to have a meeting, and for the pizza and the beer. I hope this is the start of a reinvigorated London chapter. I think the London chapter probably has the biggest membership of any chapter in the world, which is perhaps not surprising, but it's been a little bit dormant for a while, and I'm hoping that there'll be lots of events like this that we can come to. I notice that you're all behaving like typical Royal Holloway students, in the sense that you're all sitting in the back rows instead of so if you want to get close to the action, there's a lovely row of seats in the front here. But the slide should be more or less visible from the back. So they asked me to come and give a talk, or rather they asked Royal Holloway, can you provide some speakers for us to get things started again? I put my hand up, and I think most of you know, or those of you who know me already know that most of my research is in cryptography, and I offered a talk about cryptography, and they didn't say no. So you're going to get a talk on cryptography, okay? I'll try to make it as painless as possible. Just to get a feel for how many of you did the Masters at Royal Holloway? Okay, and if those of you who did, how many of you passed the crypto module? Okay, did anybody's hand go down? I don't think so. No? Well, one or two.
You're not
okay,
talking
fine.
about the advanced one.
Not the advanced crypto, basically. Crypto and security mechanisms, I think it was called, right? And one without actually very much crypto in it. Yeah, okay, good. Don't worry, we're not going to do any serious maths tonight. Okay, so I thought I would talk about how cryptographic algorithms die, and the question is, well, how do they die? And the answer, in general, is slowly, if ever. Okay, and, well, we could now go and drink more beer, or we could explore this in a little bit more detail. And what I thought it would be interesting to do is look at the story of the RC4 stream cipher, which has been around for decades, is still in extremely widespread use, but its use is becoming more and more indefensible. Something harder to maintain is secure in a wide range of contexts. And at Royal Holloway, we've been doing lots of research that's partly driving this, this new message about RC4 no longer being fit for purpose. Okay? So, as I mentioned, it's been around for a long time. It was designed by Ron Rivest. Rivest is the R in RSA. That's a throwback to your crypto course. It was designed in the late 1980s when computers were slow and had small amounts of memory. It became public in 1994, so it was originally a proprietary algorithm, and eventually the source code was reverse engineered and the algorithm was published, and actually RSA eventually confirmed, yes, this is the RC4 algorithm. And it's a stream cipher. So, okay, quick quiz. What can you remember about stream ciphers? What do they do? Anybody in the audience?
The XOR.
The XOR with the plain text, right? So we're going to generate some, what are we generating from a stream cipher? The key stream. Okay, we're generating a key stream. What properties do we want the key stream to have? What should it look like, ideally? Yes. Of course, it's not random because it's the output of an algorithm. So it cannot be actually random, but we can hope that it appears to be random. And formally, we hope that the outputs of the stream cipher are pseudo-random. Okay, and we can give a formal definition for that, but this is not the place to do that. It's a beautiful little stream cipher. It's a very elegant design. You can implement it in about 10 lines of code. It's very fast in software. It has a low memory footprint. It needs about, well, it only needs 256 bytes of memory to implement it. So it's very, very compact, very elegant. And because of this, and because actually there weren't many alternatives available, and because it was designed by Ron Rivest, and because it was the 1980s, it became very widely adopted in secure communications protocols. So TLS, this is your secure sockets, the thing you get, the browser lock when you buy something from Amazon. In 2013, about half of all TLS connections were protected using the RC4 stream cipher. Okay? Very widely used in WEP, which is your encryption for your home wireless network. In the successor to WEP, WPATKit, we're still using RC4 in protocols like Kerberos and MPP. I don't know, has anybody here heard of MPP? No, mostly shaking heads. There's one person shaking his head, so I'm now going to put him on the spot and say, what is MPP?
It's the multi.
Ooh, close, close. M stands for Microsoft. It's the Microsoft point-to-point encryption or exchange. This is a kind of a proprietary Microsoft protocol. It's actually in an RFC. You can find the details of it, and it uses RC4 in a particularly brain-dead way. But we won't talk any more about MPP tonight because it's not that interesting. We're really going to focus on TLS actually. Okay. So here is the algorithm on one slide. I should mention at this point that I think this slide was made by Jakob. Is that right, Jakob? So let me introduce Jakob Schultz. Okay, welcome. Jakob is not an alumni of the ISG, but he, or alumnus, I should say, using my Latin properly, but he was working with me at Royal Holloway for a couple of years as a postdoc, and now he's in Japan, and he happens to be visiting London this week to do some collaboration with me, and so I dragged him along this evening. And Jakob was instrumental in helping us do these attacks on RC4 that I'm going to talk about tonight. So this is very much a presentation of joint work with myself and Jakob and other people too. So while I've been saying all of that, you've memorized RC4 stream cipher, right? There it is. And the action is really happening over here. I'm not going to go through it in detail, but basically you've got some counters, you're updating your counters, you've got a state table S. This is just a permutation on the bytes, so it's a table of size 256, and you're doing some swapping of the values in the table, and then you've got some way of looking up the table to produce a value Z, which is a byte value, and that's the output of the stream cipher. So that's one byte of the key stream. Okay, and we're doing this over and over and over again to generate all the bytes of key stream, and then, as was said, we're XORing that with a message to do the encryption. Okay, nothing could be simpler. Beautiful. So many of you know the story already of RC4 and WEP. If you took my course on network security at any point in the last 15 years, you would know that RC4 is already broken. So why are we here? Why are we bothering with this talk? Well, yes, there was a famous paper by Fleurer, Mantan, and Chenier. S is the S in RSA, in which the way that RC4 was used in WEP was completely broken, okay, eventually. And now, actually, the state of the art is that you can do a full key recovery attack. So you can recover the secret key with a small amount of network traffic, something between 10,000 and 20,000 packets. Of course, these packets, you can sniff them trivially off the wireless network, right? So, and there's even tools to generate extra traffic for you, and so on and so on. So this is completely broken. So we're done, right? Well, actually not quite, because this isn't a flaw in RC4 that's being exploited here. It's a flaw in the way that RC4 was used in the WEP protocol. I guess it's probably not worth going into the details here, but basically, you could still defend RC4 as an algorithm, even though its use in WEP was completely demolished. Okay? So, for example, the successor to WEP, WPATKit, still uses the RC4 algorithm for doing all the encryption, but instead of generating the key in the way that WEP does, it does it in a slightly stronger way. It's supposed to provide extra protection against attacks. So WPATKit was only meant to be a kind of very temporary successor to the WEP algorithm until we could get better hardware, until we could get WPA2. But there was a survey done 2 years ago now in the city of Leuven in Belgium. Many of you will know there's a very good security research group in the Catholic University of Leuven in Belgium. And they drove around Leuven in their car doing war driving. Okay, war driving is not trendy anymore, but they wanted to get the data for their paper. And they found something like 19% of all networks are still using WPATKit today, okay, as the default encryption algorithm. So even though WT-KIP's still using RC4, and maybe isn't very strong, it's still in widespread use. Okay, so RC4 isn't broken, but its usage in specific protocols like web is certainly broken. So what happened after all of this? Well, it's kind of interesting. In this kind of period of time, after the Flurer-Mantan-Shamir paper, a lot of the research focus, people like me, were trying to make these attacks better, to reduce the number of packets you need to do the attack. So in the initial version of the attack, you needed something like several million packets, and as I showed in the previous slide, the state of the art is now something like 10,000 or 20,000 packets. So the attacks became more practical. Didn't stop people using web. You might wonder why that is. People then started to analyze the algorithm itself, not the use of RC4 in web, but the general algorithm. And a lot of people started to look at the key streams themselves. Okay? So you answered the question when I said, what should a key stream look like? You said it should look pseudo-random. Okay? The key streams are made up of bytes, byte values. So if I pick a position in the key stream, let's say position 10, okay, and look at the byte values that I get in position 10 over lots and lots of different keys, what distribution should I have on the byte values? What should it look like? Uniform, exactly, right? I should see every possible value of the key stream byte between 0 and 255, or 00 to FF, if you prefer hex, roughly equally often. Okay, they should each occur 1 over 256 at the time. And what people discovered was that actually for RC4, that's not true, particularly in the early positions of RC4 key streams. So the first few output bytes, like if you go back to this algorithm, when you first start running this loop, okay, and the table S has been set up by the key scheduling algorithm, there are some kind of abnormalities in that table. It's not very uniformly distributed, and those abnormalities, those deviations from uniform, start to show up in the key stream. Okay, and the classic result here was again, Mantan was involved. Mantan and Shamir showed that if you take the second byte, that's Z2, okay, so the output bytes are numbered Z1, Z2, Z3, and so on, it takes the value 0, or 00 in hex, with probability 1 over 128. What should it be? 1 over 256. So it's occurring twice as often as it should. Okay? And at that point, Mantan and Shamir said, victory, we've broken RC4, let's all go to the pub. And actually, the reaction of the applied community, or the user community, the developer community would say, well, what we'll do is we'll throw away these initial bytes, because they're obviously weak. And so we won't use them. Okay? People also found long-term biases. So these are biases that don't run out after the first few hundred bytes, but are persistent throughout the key stream. Already in 2000, Flurer and McGrew showed that there were biases in adjacent pairs. So for example, 0 followed by 0 occurs with probability, it should be probability 2 to the minus 16, 2 to the minus 8 times 2 to the minus 8, but it's actually something like 2 to the minus 16 plus a little extra, 2 to the minus 23. Kind of small little deviation, okay? But it's not quite as it should be. And then there's a very nice paper by Mantan from 2005 where he also identified some long-term biases. But really nobody knew how to use these or thought about using these in practical attacks. So we should throw away the first bytes of output because they have these funny biases. When we use RC4 in TLS, what do you think it does? Do you think it throws them away or not? Who thinks it would throw them away? Because that would be the really sensible thing to do, right? You'd be following best practice by doing that, right? Hands up. Nobody. Okay. Oh, one guy. Well, thank you. Thank you. You're wrong, I'm afraid. I tricked you. I tricked you into putting your hand up. No, it doesn't throw them away. It uses them. Why would you use these early bytes to encrypt? What possible motivation could you have?
Speed.
Yeah. Because it's crazy to set up your algorithm, start generating key stream bytes, and then not use them, right? Because you're kind of wasting bytes, you're wasting computation. And if you're trying to establish many TLS connections very quickly, you don't want to do this extra computation and not use the bytes. It's too tempting, right, not to use them. And anyway, you know, these kind of deviations from random are very small, so what the hell? Okay, nothing could possibly go wrong. So, let's talk about RC4 in TLS a little bit. I'm not going to go into the details of how exactly RC4 is used in TLS. Basically, it's what you think. You generate key streams and you XOR them with your TLS plaintext, basically, which is like your HTTP traffic, for example. So there was this thing called Beast, and then there was this other thing called Lucky 13. Sorry about that. And basically those are attacks against the other encryption option that was available at that time in TLS, CBC mode. Do you remember CBC mode from your crypto lectures? Yeah, people use it in the real world. It's a great mode. It's great for people like me because there's lots of easy attacks against it. And because of those attacks, people said, oh, you know, we should switch to using RC4 because there's no weaknesses in RC4 that we know of. Well, there's these small issues, but they're not really very serious, so it's going to be okay. And we found this stat. There's a beautiful website called the ICSI Certificate Notary. And what they do there is they track the usage of TLS in the wild. So they probe the internet, they gather lots of TLS statistics, and you can find that in January 2013, so before we announced our attacks, about half of all the traffic that was TLS protected was using RC4 for the protection. Okay, so it's like a 50-50 split. And it had been less, but then along came Beast and Lucky 13, so RC4 went up and CBC modes went down. Okay, so what did we do? And this is where Jakob comes in. So Jakob is the S in ABPPS 13. That's a reference to a research paper that we wrote. We're not very smart, so we didn't really know how to come up with new biases or find new weaknesses in RC4. So we just switched on our computers. And we took 2 to the 45 random independent keys for RC4. 2 to the 45 is a big number. It's probably bigger than we needed, but that's what we did because we had the computational power. And we computed the key streams, and we computed the distributions of the bits in the key stream. Remember, these should be uniform, maybe they're not uniform. Okay? And actually what we found was a lot of new biases in the RC4 key streams. That itself is not an attack, finding these biases, but I'll explain how you can turn that into an attack in a minute. Okay? So let me show you some pictures. Here is the key stream distribution at position 1 in the output. So this is Z1, the first output of RC4, and it should be, well, you tell me, okay, so we're starting with 0 over here, and we're going all the way up to 255, and that's the byte value, the value of the output, okay? And on the y-axis is the probability that we see that value. So what should you get if this was a good stream cipher? What should the line look like? It should be a straight line across, right? At this value, 0.003906, which you all know is 1 over 256, right? So there should be a straight line. But what the hell is this? You know, there's all kinds of weirdness going on. And all these little spikes, that's real. That's not just noise. Because 2 to the 45 key streams is such a vast number that even at that tiny, tiny scale, that's real behavior. Okay? Not just statistical fluctuations. So that's position 1. Here's position 2. And this spike here at 0 is actually on the, how high does this building go? How many floors does it have? Yeah, it's above the top floor of this building. Okay? That's, well, you know what that bias is. This is the second output bias. This is Z2. This is the Manton-Shamir bias. Okay, so Manton and Shamir already showed in 2000 that Z2 was biased towards 0 in the sense that 0 occurred with probability 1 over 128 instead of 1 over 256. And the scale of this graph means that that's way off the, up in the stratosphere somewhere. Okay, but then you go to position 3, position 4, and now you see a pattern emerge. Okay? There's kind of, the sort of gross behavior is that you have a bias at value 0. So value 0 occurs a little bit more often than it should. There's a bias at position, here it's position 7, position 6, 7, 8, and you see it moving along, yeah? As I flip the slide. So there's a bias towards position 0, a bias towards position R, let's say, in output byte R. And then there's this kind of behavior at the end where the tail is going up. Okay, and you can see that kind of consistent slope up. So we should have a straight line here, but it's all slightly off. It's off kilter. And you keep going and you think, oh yes, I know exactly what's happening here, and then that happens. You're like, what the hell is that? And it turns out though, that this bias was also already known. It was discovered in 2011 or 2012. And this is a key length dependent bias. So the value here is actually 256 minus 16. It's 240. Okay? And that's related to the length of the key. We're using a 16-byte key because that's what TLS uses. TLS uses 16-byte RC4 keys. 256 bits. No, 128 bits. Okay? So there's a big bias here towards the value 240 in position 16. Okay. Now it goes back to normal. and you think, fantastic, I've got a handle on this, I can at least kind of have a safe bet of what's happening. And it's, you notice that the spike is getting slightly lower in height all the time, means the bias is getting smaller. And then that happens. We still don't know what's going on here, but I would emphasize again, this is real behavior, okay? So I call this the dog curve, because these are the ears, you know? And then it's kind of spiky, and then that's its tail, right? So this kind of thing going on. And you see there's a kind of a parity shift there, and if you look very carefully here, it goes from odd, even to even, odd, where the little kind of peak is, and who knows? We don't have an explanation for that. And then this happens. Now this is 2 times 16. And this position here is actually 224. So it turns out this is a brand new bias that we discovered. It's a kilo-length dependent bias, where now it's at twice the kilo. And you can carry on like this. And if you want to do it all in one nice picture, here it is. This is a heat map. And what this shows in a kind of color form is the size of the biases that you have in each position. So now we have the position along the bottom. So position 1 to position, well, we looked at the first 2, 5, 6 positions. On the y-axis is the byte value now. And the color encodes how strong the bias is. How far away are we from 1 over 2 to the 8? So red means strongly biased, and blue means flat, right? It's the value that you expect. And what you see here is that the value 0 is always biased in every position. Okay? That corresponds to this spike here. This line, this is the I bias or the R bias, and that corresponds to this spike, which is moving along. Okay, if you look carefully at this picture, you can see some red dots coming down. I don't know if you can see them at the back, that's why you should sit at the front. Okay. You can just see them maybe, and that's the key-length dependent bias. And again, it's getting smaller as you go further out into the key stream, but it's definitely there. Okay, so that's a complete picture of the information you get by averaging over 2 to the 45 key streams. Giant took several months of computation on several dozen cores in parallel. The computation was done on Dan Bernstein's machines in Chicago, and it turns out that Dan doesn't have to pay any electricity bills for his lab, so that's why we did the computation there. Also, he had the machines. Okay, good. So what? There's all these biases. How can you use them in an attack? That's the big question, right? So far, it's just academic. Well, think back to that bias we saw, the Mantan-Shamir bias, that says you get 0 in the key stream in position 2 more often than you should. Think about the encryption process. How do we encrypt the second byte of the plaintext? What do we do? We're going to XOR with that keystream byte, right? But that keystream byte is 0 more often than it should be. So what that means is that the ciphertext is equal to the plaintext XOR with 0 more often than it should be. So the ciphertext is equal to the plaintext, right? Plaintext XOR 0 is plaintext more often than it should be. Okay? Now, so if you imagine a scenario where, by some magic, you can get the same plaintext repeated over and over and over again under different key streams, you can make the plaintext fixed. So P that you're targeting would always be the same value. So now if you look across all of your ciphertexts, look in position 2, the value that occurs most often is a good candidate for the plaintext. And that's it. Okay? So that's how you would use the Mantan-Shamir bias, where it's huge and it dominates everything else that's going on. But that's the kind of basic idea of how to exploit biases. But in this situation where the same message, the same plaintext gets repeatedly encrypted over and over again, several tens of thousands of times. That's how many you need, about 2 to the 14 to exploit the Mantan-Shamir bias. Okay, so what we do in our paper is we go one step further, quite a big step I think, and we actually use something called Bayes' theorem to derive the right statistical procedure to turn bias information into plaintext guesses. It's a little bit technical, but so I'm not going to do it here. But it's an extension of this idea of looking at, well, the idea would be, okay, let's guess what the plaintext byte is across all of our ciphertexts in some position. And then, if we XOR all of the ciphertext with that guess for the plaintext, we should get something that looks like the keystream distribution. because plaintext XOR ciphertext is keystream. But we know what the keystream distribution should look like. It looks like this in some position. So what we then do is say, well, which one gives us the best match for some definition of best? Okay? And that's where Bayes' theorem comes in. It's basically doing something called maximum likelihood estimation. It's a sort of standard statistical trick. Okay? And it works. It works quite well. So what I want to do before I show you the experimental results is explain how you could make everything, arrange everything nicely in the context of TLS to make a realistic attack. Okay? And here's the idea. So we're going to make the target of the attack here's Alice, poor Alice in her lunch hour, using the computer. She's surfing the internet. And the target of the attack is going to be her cookie for goodsite.com. Okay? You know about HTTP cookies? Vaguely? These are values, they're bit strings or byte strings that are sent from Alice to goodsite.com every time Alice connects to goodsite.com. And if the attacker could get those cookies, then he can log in as Alice. He can be Alice as far as goodsite.com is concerned. Okay? So we get the cookies, we win. Now, Alice is an innocent web user. She clicks on a link in an email, and that link takes her to badsite.com. And what badsite.com does is it loads some JavaScript into her browser. Okay? So now actually we have the attacker in the browser running JavaScript persistently in a tab in Alice's browser. Now that JavaScript came from badsite.com, so it cannot directly access the cookie. It would like to, but it can't directly get at it because of something called same origin policy, SOP. Okay? SOP also applies to cookies as well as domains. Okay? But what the bad guy can do now is, well, let's say first of all, every time Alice connects to goodsite.com, a TLS secure channel will be established using some key exchange and so on, and then the cookie will be sent early in the flow in the HTTP messages. Okay, because it's a secure cookie, it's only ever going to be sent over TLS. But the bad guy can also make connections to goodsite.com. The JavaScript can make connections to goodsite.com even though it came from badsite.com. Okay? Because that's the way the web works. Don't ask me exactly why, but people want to be able to do things like run third-party JavaScript and then fetch adverbs from another website or something. Okay? The web does that. It's crazy. So now you've got this guy able to make as many connections as he likes to goodsite.com. And every time he makes a connection, the cookie is attached and sent over the TLS secure channel. Which means you have the same plaintext, the cookie, being encrypted over and over and over again on under different keys. Now the active man, the man in the middle attack here, the man in the middle attacker, has to listen, gather the traffic, get all the ciphertext, and then do the statistical analysis. But what he also has to do is he has to actively break the connections here. Because what we need in the basic version of the attack is that every cookie needs to be sent in the first part of the key stream, because that's where these biases are that we were talking about before. And we need to get encrypted versions of those cookies over again with the biased key streams. Okay? So we've got a man-in-the-middle attacker that's listening in to the connection, also forcing the connection to be terminated. You can do that by just injecting a fin packet for the TCP connection, for example. And we've got JavaScript running in the browser. So it's a pretty powerful attack model. We've given the attacker a lot of capability, but we actually did this in the lab. You can set this up, and it's quite realistic to arrange all of these capabilities. Okay? So what I hope I've convinced you of is that it's sort of, maybe it's not fully realistic, but you can arrange for everything so that you can carry out the attack. Are you convinced? Good, because I'm cheating completely, but I'll explain why in a minute. So we'll get there. We'll get there. Okay, so what happens if you try this attack? What is your success probability if you encrypt 2 to the 20 times and then do the statistics? Well, it depends where you are in the key stream, or rather where your plaintext is in the sequence of bytes that are being encrypted. So let's go up a little bit. With 2 to the 21 encryptions, or 2 to the 21 connections, if your plaintext byte was in position 32, you would get it with success rate about 35%. If you were in position 16, you're already up at 70%. Why is the success rate so high at these positions? Can anybody remember? multiples of the key length. And that's where the big biases were. The big spike that was marching down from the right-hand side. Big biases mean less ciphertext required to recover the plaintext because you've got more statistical information coming through in the ciphertexts. Okay? And as you increase the number of connections, so the success rates go up, and you see that we're always doing well in those multiples of 16. And eventually, when we get to 2 to the 32 connections, so that's 4 billion, it's quite a few connections, takes a while, you've got pretty much 100% success rate across all of the first 256 positions. But already with only, say, I don't know, 2 to the 26 connections, if your plaintext byte that you were after was in position 96, you're at 95% accuracy of recovery. There's a question there.
Would it help if you varied the key length, the RC4 cipher you mentioned earlier?
You could vary the key length, and you could maybe make it so that those big biases don't occur in the first portion of the key stream. But TLS uses 128-bit or 16-byte keys, and that's fixed. So if you want to make that, as I say, a countermeasure to these attacks, you'd have to change the entire internet. Well, no, you'd have to change the way the TLS is deployed in the entire internet, which means changing every browser and every web server. And that actually isn't practical, unfortunately. Okay, good. But thanks for the question. I want to show you this animation again because it took so much effort to make it. It deserves to be seen. Thanks, Jakob. It deserves to be seen twice. So, I mean, think about you do these experiments, 2 to the 20 connections, but you do each experiment maybe 256 times to get decent noiseless, to reduce the amount of noise in the data. That's a lot of TLS connections that you're working with, or encryptions anyway, in a simulation. So let's do the animation. You see the success rate rising as we increase the number of connections, and the statistics kick in, and no matter what position you're in the first 256 positions, you recover the plaintext. Okay? However, I've been lying. Because we can only target plaintext data that's in the first few hundred bytes. So basically, beyond here, those biases I was talking about, they don't really exist anymore. So you can't get the attack to work. The bytes are pretty much uniform. Okay? How am I doing on time? Good? Okay, I'll keep going. Excellent. So, if you look at a modern browser, it doesn't send the cookies in the first few hundred bytes. Modern browsers are extremely noisy, and they send all kinds of garbage and crap in the first few hundred bytes about capabilities of the browser and which, which encoding rules it's going to use and which alphabets it supports and whether it's, all kinds of nonsense, right? So the cookies that we're after are further down the key stream. So this attack doesn't work. You might be able to target passwords. You might be able to find applications that send passwords early enough in the key stream that you can target them. In fact, IMAP does that. Okay? And basic auth also does that, as we'll see. Okay, so what we also did in this paper, because we realized this attack didn't actually work, was we came up with a second attack, and we exploited these Fleur-Magru biases that I talked about. Now, the beautiful thing about these biases, from an attacker's perspective, is that they exist all the way through the key streams. They never run out. But they're smaller. Okay? So you need, instead of 2 to the 26 or 2 to the 28 ciphertexts, now you need about 2 to the 34. Okay, so you need, what is that, 16 billion ciphertexts, roughly? That's more than one ciphertext for every IP address in the entire IPv4 address space or something, right? It's a lot of ciphertext. And we estimated the running time would be about 2,000 hours for the attack. So 2,000 hours is how many weeks? There's 168 hours in a week, so it's like 14 weeks or something. And that's with your browser constantly churning in the background, generating all these ciphertexts, generating lots of nice attack signatures, right, for an IDS. Okay? Okay. One thing, though, is that this attack doesn't need the man-in-the-middle attacker to break all the connections, because it's exploiting these long-term biases. So you can just make lots of GET requests for your JavaScript, and every one will be somewhere in the key stream. As long as you know where it is, you can target the cookies. So it turns out to be faster, because you don't have to eat the cost of establishing all the TLS connections. Okay, so this got a CVE, 2566, 2013-2016, and the score is 4.3. Does anybody know the significance of 4.3 as a CVE score?
Just on the cusp of the PCI DSS.
Ah, fantastic. Do you want to explain to everybody what that means?
So they probably know what we do, the two-path PCI DSS lets you got to have no CD, no probability of CVE is higher than 5?
4.
It's higher than 4.
It's 4.
Yeah.
So this is above the threshold where you can no longer be PCI DSS compliant. Okay. Actually, when this attack was first released, the CVE score was lower. It was 2.7 or something, which is not very high, right? And it's because it's a very tough attack to do. 2 to the 34, 2,000 hours is a long time. But then another attack was released earlier this year, which I'll maybe talk about in a slide or two, and everybody got all excited about it, and so they gave it a high CVE score, and then they realized that their attack was worse than our attack, in the sense of requiring even more ciphertexts. So they had to go back and revisit our CVE score too. So thanks to a crappy attack, our CVE score actually went up. That's a win. That's a win. Okay, so this work in 2013 got some media attention. I don't know if you follow Ars Technica or the Register. 2 new attacks on SSL decrypt authentication cookies. Pretty accurate. 2 attacks, single byte, double byte. Only one of them actually decrypts authentication cookies, but you know, okay, I'll take that. That's good. That's a win. Here's the Register. HTTPS cookie crypto crumbles again in hands of stats boffins. If you write for the Register, you're contractually obliged to call any scientist a boffin. It's a requirement of the job. Okay? And I complained about this to the editor-in-chief of the Register, because I'm not a boffin and I'm not a stats boffin. I'm a cryptographer. Okay? Get over it. And actually, they said, oh, but that's our house style, and we think it's inclusive, and people seem to like it. So then I a list of 20 pages from the web where scientists were complaining about being called boffins, to try and educate them about the fact that they haven't changed anything. They're still calling us all boffins. Okay. But the sub-headline, keep calm and carry on ciphering with RC4 for now, is pretty accurate. Because what this is saying is, well, this is not good, but it's not the end. It's not deadly. Maybe you should start thinking about migrating away from RC4. Don't panic, folks. And then there's this guy. Some of you may have heard of Bruce Schneier. If you don't know who he is, you just click on About Me, and you get lots of marketing about how great Bruce Schneier is. But he has this very nice blog, and actually he described it as a really clever attack. So I'm a big fan of Bruce Schneier. Because it's really clever. Actually, it's not. It's basic statistics plus switching on your computer. But okay, fine. So we got lots of coverage. So then what happened? Well, this is from a year and a half after our attack was announced. This is December 2014, and this is the distribution of cipher suites that's being used in the wild. Okay, this again from the ICSI certificate notary, and I cut and pasted this chart from their website. And here's all the RC4 cipher suites. Okay, and if you add it all up, it's about 35%. It was 50, now it's down to 35. I want to show you something, though. I think this is really interesting. Again, if you sat at the front, you'd be able to see this more easily. RSA null sha. What the hell? Which one is that? I think it's this one at 4.6%. Wow.
Are those
So
the
no
ones that are
cipher.
actually being used, Kenny, or they're the ones that are supported when they actually program servers?
No. This is not based on probing servers and seeing what's supported. This is based on measuring live SSL traffic that's being set up and negotiated using, some client connected to some server with some kind of distribution. So it's real
They're
traffic.
taking off tap points.
Sorry?
They're taking off tap points.
Yes, they have tap points, exactly. Exactly. What do you think this is?
You had a thing from Polish, because Ristic did quite a lot of work.
Yeah.
So he does a server check page.
Yeah.
Has he changed the way that works?
I'll talk about that in a minute. I'm coming to Qualys and Arsenal and what they've said about RC4. I think in some detail. The question is really, what's all this null traffic not using encryption? Maybe it's software updates. Not completely clear. Okay, so we went from 50% to 35%, but it's not dead yet, right? And that's not good enough for me. Okay. If you look at SSL Pulse, which is what Dave was talking about, still in February 2015, so less than a year ago now, 74% of the 150,000 sites they surveyed still support RC4 cybersuites. So a browser can still select them if you want to. And actually, another survey from February 2015 says that nearly 1% of 400,000 sites only support RC4. You can't select any other cybersuites except RC4 cybersuites. Okay, that isn't good enough. Then in January 2015, this happened. This is the IETF reacting to our attack only 18 months after the attack came out. But actually, that's quite fast for the IETF. they've done pretty well. They're getting that done in that time. And what it says is that TLS clients and servers must never negotiate the use of RC4 cipher seeds, essentially, right? So it says don't use RC4 anymore. And what's really nice is it directly cites our research, which is really cool. That's a win, right? That's fantastic. It's a win as an academic that an RFC cites your research as a reason to stop using RC4. But of course, that doesn't stop people using RC4. That's more like a best practice recommendation, or a warning from the future, or something. Start thinking about migrating. Okay, then what happened? So in this 2014 paper, Jakob and I and another colleague applied these ideas to WPAT-Kit. That was that successor to Web. And what we found is that the biases are even bigger. Okay, because of the way that the key is built in WPAT-Kit. So the attacks are even more severe there. Then in 2015, this is me with a couple of PhD students, one from Royal Holloway, one from Johns Hopkins. We refined the attacks from so this is like now the second generation. This is trying to push harder to reduce the amount of ciphertext that you need. And here we focused on passwords, and we got it down to 2 to the 26 encryptions to recover a password with about 350 hours of network traffic needed. Okay, so 2,000 down to 350. I just need 5 minutes more. Don't worry. You're looking at your watch now.
No, I was looking at the door.
Ah, okay. All right. Then there's this attack, the bar mitzvah attack, which I mentioned, and this is Mantan again. So Mantan now works for kind of like an Israeli kind of software company who are interested in kind of like marketing and making a big fuss. So they put out this kind of PDF document that contains this bar mitzvah attack. And what he had was a presentation at Black Hat Asia, and the abstract sounds really amazing, right? It sounds like this is RC4 dead, it's killed, dead in its tracks. And it was a very cleverly written abstract, because he didn't lie in the abstract, but he was economical with the truth, let's say. Okay? So this is the attack that had the high CVE score that turns out to be worse than our attack, right? He needs 2 to the 30 connections to recover an early byte. We need like 2 to the 26, already 2 years ago. So anyway, never mind. And then there's this very nice paper by Van Hoof and Piesens. These are the guys from Leuven that I mentioned. And they took the ideas from our paper, and then they souped them up, and they used these long-term Mantan biases, and they got it down to about 2 to the 30 encryptions. So we needed 2 to the 34. They're now down to 2 to the 30. And their attack only takes 75 hours, whereas ours took 2,000 hours. Now, they got a factor of 4 speed up in their attack by using a faster browser. Right? But that doesn't matter. If you're in the press, all you care about is this number here, 75 hours. Okay? That's the headline. That's the thing that hits the headlines. Okay? Yes?
It's a bit of history there, because that's the definition of a cryptographer from the first Bletchley passport. To break the code as quickly as possible and for it as well.
Yeah. But, I mean, our attack could have been 4 times faster if we'd used a faster browser. There's nothing clever in the cryptanalysis there. It's about using a machine running on a faster processor. And maybe using Firefox instead of Chrome. Yes?
75 hours there. What use is cookie recovery after 75 hours?
When I log into Facebook, I'm a Facebook user, sorry, from my laptop, I never ever enter a password. It's because it's got long-term cookies, persistent cookies, lasting for months, maybe even years. I don't know what the lifetime of them is, but I've never looked, but it must be months and months. Yeah. So 75 hours is actually starting to get quite worrying. You still have to do 2 to 30 encryptions, so you're still generating huge amounts of network traffic, actually gigabytes still. But you can see the direction of travel. That's where we're headed. Okay, so there's more media. Now we're angry secure bots rather than what was it before? Yeah. Okay. Ars Technica gets it spot on again. This is not an advert for Ars Technica, but this guy Dan Gooden, he knows what he's talking about. It's well worth reading his articles. They're pretty accurate and correct. Of course, he was carefully briefed by me before he wrote his article. That's by the by. And then boffins again. There we go. But this is a reference to the boffins from Belgium rather than us. I mean, they really are boffins. We're scientists. We're scientists. But what I wanted to point out here is there's the headline, there's the subline WPAT-Kit, And then there's this number, an attack that can be executed in 52 hours, and that's how fast the attack was. Not how much ciphertext does it require, how practical is it? It's the amount of the wall clock time required to do the attack is the key consideration. Okay, so where are we now? Well, it's slipped down the agenda. Here's the RC4 cipher suites to, as at August. Look at this though. 14%, 13.8% is null SHA-256.
How?
What the hell is that? I think it might be to do with the release of the new Windows, new version of Windows. Maybe that was all being streamed. I don't know. I'd really like to know what that was, but if anybody's got speculation about that, tell me. Tell me afterwards. Okay, good. So the traffic went down to about 10%. Then it popped back up again because this 13.8% disappeared and then proportionately it went back up. So 13%, 15% is kind of...
Check this slide back again.
Yes.
So triple des made a return.
Where's that?
The third
There?
one down, yeah.
Yeah? Yeah, but it's, what, 5% or something?
Yeah, I wasn't
Pretty
there.
small.
I was looking at it because one of the supported browsers, when they got rid of RC4, they slipped in triple des instead.
Instead, right.
Yeah.
Okay, interesting. So there's a bit of a kind of a war going on here, people trying to maintain old versions of TLS that only support RC4 or CBC mode. What's the least worst option? Well,
Yeah.
they're all terrible, but there we are. Okay, yeah, so coming to the end. Okay, I think the big win is this. September the 1st, 2015, a coordinated announcement for Microsoft, Google, and Mozilla saying that they will fully disable RC4 in their browsers from early 2016. Thank you very much. Thank you. And indeed, okay, so that is something to celebrate, because if you disable it client side and people regularly update their software, okay, that happens automatically for Chrome, for Firefox, not so automatically for Microsoft, but people are still using 95, I believe. Crazy people. Anyway, eventually we will see the end of RC4 at least being asked for from the majority of the clients. Okay, so the very end then. RC4 has a long and happy life, and it's now heading for the retirement home, where all good algorithms eventually go. The death of RC4 and TLS has been very slow and very painful, and you can speculate about why that is. I think the first point I'll happily admit is that the first generation of attacks were not really very practical. They were more indicating there may be trouble ahead. Okay, start playing music now, there may be trouble. Direction of travel is clear. IETF took a while to get its ducks in a row and issued their document deprecating the use of RC4. It took them about 18 months, but you know, these things take time. And of course, there's this issue that all of this is happening in this kind of little bubble in the IETF, in the academic community, but there are hundreds of thousands of website administrators out there who don't have time or energy or education to read RFCs and think about how to reconfigure their servers. Okay? And then there's also this issue of legacy. The websites do not want to lose traffic, they don't want to lose any customers, so they want to support all browsers for as long as they possibly can.
That influences your second to last bullet point, because website admins might want to change it, but they're being told not to.
Maybe they're told not to as well. And actually, yeah, a colleague of mine in the industry gave me a very compelling scenario where a large company with a lot of kind of terminals in shops, purchase terminals, couldn't change the algorithm because there's no mechanism to update the operating system or any of the supported services. Still, I think we're just about merited there to crack open some champagne. I think we've made a lot of progress. Okay, so that's all the slides from me. I may have questions, or I'll be happy to help start some discussion. Comments, questions? Stunned silence. That's also an alternative. Beer? Yeah, go ahead.
Okay, so PCI has also announced as of June 2016,
Yeah.
you should no longer be using TLS 1.0 as well.
I think we were discussing it. I think it's SSL3 that they're banning.
They've stated SSL and low versions of TLS.
Okay.
When I've spoken to my QSAs, they go, that's 1.0.
Yeah.
What?
Probably 1.1
I said,
as
where,
well.
well, they just said the low versions of TLS. I said, is that 1.1? And he goes, no, just...
It said versions plural of TLS.
Yes, older
It's-
versions.
That could be 1.0 and 1.1.
Yes.
That's exciting.
Uh-huh.
Does that create problems for you guys? Yeah, Nick, did you want to say something?
Yeah, I mean, I was at the PCI community conference last week, and the PCI council there were trying to figure out how to best phrase, how to say, don't use any of the old stuff without necessarily making it specific, because I think they've been caught out a couple of times now where they've said, okay, don't use SSL. Oh shoot, TLS 1.0 is broken as well. Okay, don't use TLS 1.0. Oh shit, TLS 1.1 as well. So they're trying to sort of come up with language that sort of reflects, use the most recent version. But the DSS doesn't actually specify, doesn't make it clear.
Yeah. Yeah, I'm sorry if we've created, if the research community has created pain for you, but it will be worth it in the end, because we'll end up with better security. And these attacks are not really practical. And there's a really good discussion to be had there about, you know, we're all in the game of marketing. I was criticizing Bruce Schneier for being, I mean, I'm doing the same, right? You know, here I am giving a talk. I didn't have to come this evening and talk to you all you guys from the industry about how great our research is. We're all in the game of promoting as much as possible whilst trying to stay on the right side of over-exaggeration. And I understand it creates pain for people doing compliance. It's not easy. Yeah.
With the piece, how many times was that downloaded your paper? Because you got very busy. You said something about got a new vulnerability coming up.
Oh yeah.
And you were going to keep an eye on just how interested it was.
The beast is not my attack, actually.
But you have some papers.
Do you want to read some?
Your papers that you publish on the Raw Holloway site.
Yeah.
Do you know how much traffic that generated interest?
I think we did actually track traffic statistics for Lucky 13. And I think it was like 25,000 downloads or something, which is not a huge number of pages. I mean, our server didn't break sweat, so it's not a huge amount. But most people don't consume the original research. No. They read Bruce Schneier, or they go on Ars Technica, or sorry, the Register, and they think of us as being dolphins, and maybe we are. So, yeah, I mean, there's an issue about translating research into something meaningful for people who have to make decisions. You know, you get asked a question: should I stop using TLS because of the beast? No. You just need to be careful.
The worst question I think you get is be somebody saying to you, what do I have to do?
Yeah.
Absolutely nothing. You have to do absolutely, you know, there's no rules there.
Yeah.
And they're charged by PCI or something like that, but for most people actually, you don't have to do, but they're stupid not to.
Sure. Well,
yeah.
Depends. Maybe you upgrade TLS to a new version and the software has a bug, right? Yeah. Maybe you update OpenSSL and you end up with Heartbleed. The early versions of SSL didn't, OpenSSL did not support the Heartbeat protocol, so they weren't vulnerable to Heartbleed. There's only a few in. So you win some, you lose some. And I didn't talk about all of those. I mean, there's been tens of vulnerabilities in TLS discovered. I think that's also really interesting as well. So for years, nobody really looked at TLS, and then from 2011 onwards, suddenly the academic community, the hacker community started to really dig into it and start to find all of the issues. And it's a snowball effect, right? I'm trying to think what the earliest paper was. So Beast got a lot of headlines, and then Crime in 2012, and then we did Lucky 13. And then academics realized, oh, you can write research about this thing. Let's start reading and finding out how it works. And then they found all these other vulnerabilities. So it's been a great party for the research community, but not so great for everybody else.
The communication could have been better.
Yeah.
Like understanding exactly what are the problems with TLS 1.0, 1.1, so they can make a decision. Like for updating the cipher suites, it was a pain because you look at the browsers and you ask them which ones you support, and they just say the version of the protocol as opposed to cipher suites. So remember triple S? That is one browser. That is IE8 on Windows XP that needs it, but that's actually still high enough that people are still using it.
Still seeing a percentage
of a lot of web admins or people responsible for no idea how to set up those suites. I mean, Ivan Russ is given his guides, which a lot of people are going to.
I would say in my, sorry to talk over you, but in my defense, okay, I do spend a lot of time talking to people like Ivan Rustic, who builds the Polis website, and I give him, we met for dinner when all this stuff came out, and he gave me a nice signed copy of his book, and then we discussed, okay, how are you going to configure, what are you going to say on your website about these RC4 attacks? So that information does flow from researchers like me to people like Ivan, who very much sits in the middle between and provides useful advice. So you don't want the communication from me, because I probably can't communicate it that well in the language that you want it, or your customers want it. But you want people like Ivan talking to people like me to try and make the translation. So I would defend that the communication wasn't good. I think the problem was that it was extraordinarily complex.
Yeah, no, I don't necessarily mean
Depends
with
on
that specifically.
How much it's going to cost
Yeah.
to go through all the pages.
And just going through the RFCs and going through the comments and the conversations around that, to be part of the conversations to understand where.
Sure.
And the paper wasn't reassured that it was actually digging deeper
Sure.
to understand exactly what's
Sure.
there.
And so you could, for example, criticize Microsoft for only supporting very limited numbers of cipher suites on their different, and having such a diversity of support on different versions, different OS, different browser versions, and that is entirely avoidable. Actually, you didn't have to do that. So yeah, this has been a particularly, not the RC4, but the whole TLS ecosystem over the last few years has become extraordinarily complex because there's all these attacks chipping away at different parts of it. And then what's left? Well, what's left is TLS 1.2. And that's really where you need to go to if you have the capability. If you're able to upgrade, you should be using 1.2.
There's a silver lining as well, is that you actually see very little 1.1, and that's probably due to the auto updates and so forth. So
Right.
going forward, thanks to these features, if 1.3 comes out,
Yep.
and if auto updates soon, then maybe that will
Smoothly transition.
smoothly transition that.
I think, though, the real reason that we'll end up with 1.3 is not security, it's performance. Because 1.3 is going to offer a very low latency connection establishment protocol, much better than TLS currently has. So you'll see faster loading of your websites, and that will push it. That will make it happen. It does bring other security enhancements along with it, so there's good reasons from a security perspective to do it, but that won't be where the push comes from.
The algorithm, the blockchain modes that support concurrency, do those help as well?
No, so it uses 1.3 will not allow RC4 or CDC mode. It will use something entirely different class of algorithm, something called AES GCM.
Yeah, GCM or counter.
Or cryptographic counter mode, but actually that won't see widespread deployment. GCM will be the thing that gets used. But GCM, yeah. Watch this space. Maybe that's a good point for me to stop. Thank you all for your attention. Thank
Shady, do you want to give a